All right. So as I was saying, when we have a non-commutative algebra, but it's almost commutative, it has this kind of filtration, I can take its semi-classical limit, which means that I take the associated graded and then I remember a little bit of the non-commutativity, which comes from this Poisson structure. So I remember sort of the next order bit of taking commutator, which was the basic operation for like how quantum physics work. And just one thing to note here, which might not jump out at you if you're used to this story. I required, so I snuck in here an integer n. So having this kind of filtration, I want that the commutator of things of degree a, I, and things of degree j. Well, in order to have commutative associated graded, I needed to have degree strictly less than a plus I plus j, but I want it to be less by some particular amount n, which could be 1, but could be more than 1. Depends how I'm feeling that day.
Why conical?
Sorry?
Why conical?
The conical, that refers to the C star action that comes from the gradient. So it's a cone in the sense of algebraic geometry. And by the way I set up my filtration will be a positive ring. So when I take spec of this ring, it's going to have a single fixed point that everything's getting attracted into.
But then you need also conditional 0. It could be like a field.
Oh, sure. Yes. You're right. I should have. But you can't see that slide, so you don't know I didn't put that. So yes, in general, it would be attracted into spec of the degree 0 one, which if you're smart, you'll assume it's all right, so this is actually a functor from filtered almost commutative algebras to Poisson commutative algebras. Yeah, and so right to have this Poisson bracket, you have to say what degree it's in, and that's why you need that. Okay, great. So if we take the Weyl algebra, well, the classical limit is just polynomials and twice as many variables. And the Poisson bracket is the actual Poisson bracket defined by Poisson, where you take derivatives with respect to momentum and position, and then swap momentum and position. And in particular, like, this should have been, sorry, I fixed part of this formula and then I didn't fix all of it. I'd originally written the one variable version. So it should read that it's delta ij. So they're conjugate in the sense of physics, conjugate variables. Another sort of slightly more interesting example is that if I take the universal enveloping algebra of G, the classical limit of that is the symmetric algebra of G, or you can think of that as functions on G dual, on the dual vector space. And that inherits a Poisson structure called the Kosten-Kirchhoff-Surya, where I think of elements of G as linear functions on the dual, and I say the Poisson bracket of those linear functions is the Lie bracket thought of as a linear function. This is one of these things it's so simple, it's hard to write the notation because it starts looking tautological. Like it's tempting to write bracket of x and y is bracket of x and y for the two different kinds of brackets, but that's very confusing. And if you've ever heard of this theorem that there's a symplectic structure on covariant orbits, really someone was trying to tell you about this Kosten-Kirchhoff-Surya structure, and they didn't want to say Poisson. So it's sort of gotten by kind of sticking together all of those symplectic structures of covariant orbits. Great. Are there any questions?
I guess just one. Yeah, this conical algebra you said is it's like a almost commutative algebra, but where the filtration splits.
No, so an almost commutative ring is a non-commutative ring that has this filtration, such the associated graded is commutative. Right. So I'm not assuming any filtration split.
Okay, so conical is the sort of thing that appears as associated graded? Of-
Yes,
Okay,
yes.
thanks.
It's the graded part of associated growth.
Okay, thanks. Yeah.
And, I should say this sort of contrasts a little bit with if you do quantization with like an actual parameter, because then you're specializing your parameter to 0. There's no reason to think you have a grading at h equals 0. But you can sort of rephrase all of this in terms of deformations using each one. All right. So, as I was saying, we have this commutative ring. We might want to think about the corresponding variety instead. That might make us feel better. And so I'm going to call that affine variety conical Poisson. Its coordinate ring has the conical Poisson structure. And the most interesting examples of these are conical symplectic varieties, which are ones where the Poisson bracket is symplectic on the smooth locus. And then there are some extra technical conditions I don't want to go into. Contraction required to add. There are extra conditions, but they really don't matter. They never cause me a problem in my life. All right. So kind of the most standard example of this is you might take a symplectic vector space, a finite group preserving the symplectic structure. Sure. Right. So the kind of example you might think about is like, I have gamma acting on Cn, and then I take the sum of that representation with its dual. Right? That will automatically have a symplectic structure that it preserves. Alternately, I could think about the variety of nilpotent matrices that has a natural symplectic structure by thinking of regular nilpotent matrices as a coadjoint orbit for GL. More generally, I could think about the nilcon of semi-simple algebra. And in this case, there's sort of a particularly nice correspondence between almost commutative and semi-classical. So to say that, I should define a quantization. So, right, we have this functor where we take an almost commutative algebra, we take its semi-classical limit, I'm writing classical limit in the slide, but it's semi-classical, it remembers the Poisson structure. And you might ask, well, can I go backwards? Can I start with something with a Poisson structure and find the non-commutative algebra? If I can, how unique is that non-commutative algebra? So for example, if I take polynomials in 2 variables with Poisson's Poisson structure, you can check that the unique way of doing that is the biology. These are slides that have gotten moved around a bit, so, but I can tell you the bio algebra. And the way to check this is to think about if I had a quantization of this guy, I can look at things of degree no more than 1, and that would be a 3-dimensional Lie algebra. And there's only one option for which non-commutative, nilpotent 3-dimensional Lie algebra it is. And once you observe that, everything else is forced on you.
That includes the quotient and the parameter n. All of that's forced as
well. I mean, I think the parameter n is built into the Poisson structure because I have a grading, and the degree of the Poisson structure is minus n. So starting with the Poisson guy, I already have n built. And so yes, at any quantization, there's going to be a filtered isomorphism to the bioalgebra. Basically, you think about the bioalgebra as a quotient of the universal enveloping algebra. It's 3-dimensional. All right, cool. So, in general, the answer is that it isn't unique. There isn't only one quantization. There can be many. But there's a nice universal family. So there's a single non-commutative algebra whose center is a polynomial one, and the quotients by the different maximal ideals of the center give you all the quantizations. And this is a theorem about conical symplectic varieties. Any one of those, there's a unique family. So for example, if I put in a nil cone, the unique family I will get out is the universal enveloping algebra of that Lie algebra. If I put in C2 mod a finite group, what I get out is what's called a spherical symplectic reflection. And you might like go to some paper and look up what the definition of a spherical symplectic reflection algebra is, but that's a terrible mistake. This is the definition of a spherical symplectic reflection algebra. And I think I kind of threw this out. So I've been kind of simplifying this talk because I've been giving it as a colloquial action, like this is sort of a distraction that I don't need. But for you guys, I will mention this. So I have my y, and there's a universal fit. Is the board going to be readable? Or should I write it on the iPad?
You could turn on the light maybe for a moment.
So I have my symplectic, conic symplectic variety. And it turns out that this guy sits inside a universal family of all of the ways of deforming this guy while keeping its symplectic structure. So for example, if I have the nil cone, all the ways of deforming the nil cone while keeping its symplectic structure gives me the full dual of the Lie algebra. All the other nil cone orbits are deformations of the nil cone. And that's the only way I can deform the nil cone and keep the symplectic structure. With this guy, what ends up happening for C2 mod gamma is for every element, every conjugacy class in gamma, which is a symplectic reflection, so it's acting symplectically, it can't only have one non-zero eigen, but it has one inverse pair of non-identity eigenvalues, and all the other ones are one. I get a deformation direction for each one of those. And that's sort of how this spherical guy works. Sorry, not just there's a little bit more going on. But the sort of thing you should think about is if I take C2 and I mod out by the cyclic group of order n acting symplectically, the equations for that are uv equals w to the L, where this is x to the, oh, sorry, n. This is x to the n, this is y to the n, and this is xy to the n. And the universal deformation of this is deform this to a generic monopolar. So that's the kind of thing you should. And note here, this is related to this guy. This is actually a type A solidity slice with some regular orbit that makes up the deformation. All right. And I should have said that, so sort of how you prove this theorem is that this universal family has a unique quantization, and that's the universal value. So this base that sort of specifies all the non-commutative deformations, it's also the base that specifies all the commutative deformations. But it's sort of one of these things where it's kind of affine space. So it's not quite that you can connect every non-commutative deformation to a commutative one, but somehow the parametrization is the same. Like here, the parametrizing space is the torus mod the dual torus mod the Weil group, and that also is spec of the center of the universal enveloping algebra, but not really quite canonical. Right? It doesn't really make sense to attach particular quotients of the universal enveloping algebra. It is a little bit canonical, but it's not that.
Yeah, like it seems like if two spaces have the same space that parametrizes them, then there is a bijection.
There is a bijection there. I mean, I am exaggerating a little bit. There is a canonical bijection between them. But it doesn't feel that. It's canonical, but you're never entirely comfortable. If you think about this example with the universal enveloping algebra, like lots of special things happen at special points of the center of the universal enveloping algebra. Whereas, like if you do this family like it's conical. So like, multiplying something by scalar doesn't change anything about it, just multiplies the volume of the.
But if I'm a symplectic geometer, maybe I believe in like Boris Sommerfeld.
Yeah. So maybe that sort of style of thing. That's plausible. That is the kind of thing you should think about. Like, it's not geometrically very different, but you're right. Like maybe some integrality on some classes in homology gives you something a little bit nicer. So yeah. Okay, great. Any other questions? Okay, so why are these things out there? So, somehow the portion of my colloquium I just did, I probably didn't, it hasn't literally not changed for 10 years, but it hasn't changed very much for the last 10 years. There's been a little bit of progress, but that's stuff I've been thinking about for a long time. And I would always hear these kind of hints from physicists that really this story, there's some physical origin behind it and some interesting physics related to this stuff. And for a long time, I really had no idea what they were talking about. And now I've gotten to like, I sort of have some idea what they're talking about, but I'm still a little confused. So I often put this picture up. I don't know if this sort of comes out in the room. This is in 1968, the physicists looking at Feynman diagrams and being excited and happy, and the mathematicians, doing algebraic topology and looking at Riemann surfaces and being happy. And then here in 1998, the boards have switched. Everyone is grayer and fatter, and no one looks happy. That's kind of my life. But I at least know enough to say this story, these sort of quantizations and symplectic varieties come naturally out of three-dimensional quantum field theories. And like all the examples I know are secretly some story about three-dimensional quantum field theories. And so I want to try to explain what little I understand about that. So hopefully you can be approximately as confused as me. So what's a quantum field theory? Well, obviously that's a very big question, but I think I kind of know a reasonable answer, which is like, it's an algebra, but it's a really big, different kind of algebra. So algebras are things where I have stuff and I multiply them. Well, in quantum field theory, you have stuff that live on different points in a manifold, and a rule for multiplying them that might have something to do with where they are on the manifold. And I mean, it really might depend on things like metrics and such. So for example, vertex operator algebras are about quantum field theories where the multiplication of operators depends holomorphically on the position. But sometimes if you're lucky and the quantum field theory gods are kind to you, you can find something called a twist. So this is an extra differential on your quantum field theory, as degree 1 and some grading on operators we're not going to worry about. And well, the multiplication of operators might change as I move points around, but it's going to change in a way that's exact for this differential. So the product on homology for this differential isn't going to change. It isn't going to depend on the positioning. It's going to be a topological. But as we all know, you have to be careful passing the cohomology of things. If you take a topological space, the cohomology of that topological space genuinely has less information than the DG algebra changes. And so similarly here, you don't want to immediately just go, okay, great, I have a product on cohomology. You should remember, well, yes, but if your points move around, you get a homotopy that depends on how the points move. And so if they move in different ways, you might get different homotopies. So I'm going to talk about the d = 2 case first, even though I want d = 3 eventually. So in a d = 2 topologically twisted theory, well, again, we have a multiplication. It depends on 2 points. After I take cohomology, it becomes a commutative multiplication. And the reason it's commutative, I'll take this off here, is that I have my 2 points, and well, they can change position. And so by doing that, I get a homotopy between the 2 ways of multiplying. Right? Moving my points continuously doesn't change what the product is of cohomology. Okay. But I had to make a choice about how they swapped places. Right? So I drew them swapping places this way, but maybe I would prefer that they swapped places the other way. And when I do that, I get a different homotopy from one multiplication to the other. And so if I take the difference between those homotopies, I'm going to get an actual chain of degree 1, degree 1. And this is what's called the Garrison-Cover bracket. So this is the difference between the 2 homotopies that come from the 2 ways of switching. Now, why did I talk about the degree 2 picture when I ultimately, sorry, dimension 2, and ultimately I want dimension 3. So now I'm going up 1 dimension. I'm going to be in d equals 3. And so again, you should think about this. I have points, or you can draw them actually as little spheres. Like I could have drawn the picture here of the multiplication corresponds to this cobordism from 2 circles to 1. So here the multiplication is going to correspond to this cobordism from 2 spheres to 1. I know my picture's not so great. So again, I can swap my 2 points. And now that I'm in 3 dimensions, what happens? Well, I can swap them the 2 ways, but of course, those 2 ways are also equivalent in my 3-dimensional space. But they're equivalent in 2 different ways, right? So I could rotate the whole plane this way, or I could rotate the whole plane this way. Or another way to think about this is that I have 1 point, I have the other point do a complete loop around it. That gives me the homotopy in degree 2. And then I have 2 ways of capping this off with a disk, depending on which side of the point in the middle I do. I'm looking at the difference between the 2 ways of homotoping that circle down to a. So ultimately, what I get now is a chain map of degree -2. And that's my Poisson bracket. So suddenly this picture I had before, I mean, if you take like literally nothing else away from this talk, take away this 3-dimensional topological field theory, but where I haven't completely gone topological. I still remember the actual chains. I still remember my differential, gives me exactly the thing I was talking about before, a graded commutative algebra and a Poisson bracket of degree -2. This happens to be n equals 2. Turns out the universe wants n equals 2. Ooh. That's just how life goes sometimes. All right, are there any questions?
So what did you say just now? The universe wants n to be
N to be 2, yes.
And
The degree of the Poisson bracket. That somehow naturally you get it, when we were talking about quantizations, I mean, most examples you either want n equals 1 or n equals 2. I didn't kind of emphasize this, but like the usual filtration on the universal enveloping algebra, you get n equals 1. The filtration I talked about on the Weil algebra, you get n equals 2. You can always get n equals 2 from n equals 1 by doubling the degree.
You studied a floor D theory when you get n equals 3.
Yes, but things would be super. It would be a super Poisson bracket. Everything is happening in super vector spaces. Yeah, I mean, so you could reasonably ask about like 5D theories. And I think the answer is there are like a lot fewer 5D theories than 3D theories.
There is 5D n equals 1 super Yang-Mills theory.
Well, maybe you get something interesting out of that. I don't know. Right. And so I should emphasize the sort of the thing you're getting out of this theory is the Hilbert space of a sphere. That's always an algebra with this cobordism that I and physicists will often call this the local operators. So I mean, yeah, when you twist, I mean, is that n equals 1 twist going to be topological?
I don't think so.
Right. So like, I think the answer is like in 5D. Yeah, I would want to talk to a physicist about it, but I think like in 2D and 3D, there are a lot more interesting examples with topological twists.
Can I ask a question about your use of the word topological?
Yes.
So so this sounds like you're describing what's left from EN algebra. And I'm used to EN algebra, the locally constant factorization algebra being topological field groups, but you said this is something that's not fully topological. So I must understand.
No, I think you are understanding. I mean, this is I mean, I don't know. I would have also said this was something that you could phrase this all in the language of E3 algebras, right? This is something about like when you take the associated graded of the E3 operad, you get this Poisson operad. Like, so you can take this as me trying to explain that fact, and maybe doing it for me. I didn't say the word E3.
But there's actually a lot more structure, right?
In the E3 operand, yeah. Yes, that's true. It's an associated gradient. So that's my best attempt to address your question. Try to talk about it. I try to do it on the fly. There's also a natural way to get a deformation quantization out of this, which is basically to insert what in physics, I mostly say these physics words, so you'll know to look out for them. If you see them in a paper, this is called an omega background. So this, you actually change the twist that you use by incorporating the action of rotation of S1 on. And once you do that, you get a non-commutative algebra. So by changing that twist, I change what the multiplication is on the cohomology, changing what the differential is. And whereas before I said, oh, I can take my 2 points and I can swap them. Well, if I'm doing rotation around a straight line, I can't swap them in a way that's S1 equivariant. So my argument that I had a commutative algebra just goes away. And in fact, you can see that there's a relationship between this multiplication and the Poisson bracket. I just kind of like this story. If you draw a 2-sphere, and you think about rotating on it, you have 2 fixed points. So you can think about this secondary product as integrating over a 2-sphere. And once you incorporate the S1 equivariance, you can do that integral by localizing to these 2 fixed points. And the contributions to the integral are the products in the 2 different orders. And that 1 over h, that's the weight of the tangent space on S2. This is exactly what we want. So sort of this whole package, the Poisson structure, the quantization, it all naturally comes out of the physics. So again, somehow, if you take nothing else away, just remember that. That's the message I have come here to speak. Anytime I have a 3D quantum field theory with a topological twist, I get almost commutative algebra, and it's classical limit. And there's a lot of mysteries here, but it's a very interesting way to construct examples and to understand what's happening. All right, so what do we want to find out about examples? What are the examples we care about, and what are we going to ask about? So another thing I'm contractually obligated to put in my talks is this claim that symplectic singularities are the Lie algebras of the 21st century. So somehow we found here that like all statements about this semi-simple Lie algebra are really statements about this nil cone. All the information in the Lie algebra is somewhere in this nil cone. And so we can take other symplectic singularities and pretend that there's a Lie algebra that they're the nil cone of, and try to ask all the questions we asked before about Lie algebras, but now about these other symplectic singularities. This is another one of these points where I cut a lot of stuff out of this talk, but somehow the thing I thought was worth kind of emphasizing is, there's this kind of remarkable fact about the representation of Lie algebras. That if you look at simple highest weight G modules, so simple modules in category O, their characters can be written in terms of Verma modules, and the coefficients are given by something geometric, given by Cauchy-Lustig polynomials, which you can interpret using intersection homology. Right. So this would be, in my mind, a great statement to try to generalize.
Can I ask a big question?
Yes,
I mean,
bigger the better.
this is all about singularities, which is good. Like all of these have minimal resolutions, and you can say anything about this.
What do you mean minimal?
I mean, like there are,
symplectic resolutions?
I don't know the right words, but there are resolutions of singularities which are nice in both of these cases. The two
That's true.
And
Yeah, I mean, that's sort of one of the things I kind of cut a little bit out of the talk. So, I mean, there's also some story where this space of deformations also kind of tells you about the space of resolutions. Right, that like the real version of this base like actually tells you what the Neff cone of resolution is. And yeah, I mean, okay, there's different talk I could have given that would have had a bunch of that stuff in it. I'm kind of trying to sweep that stuff under the rug here. But I'm happy to talk about it later. Well, I mean, there's a very interesting question, which is how do you find those resolutions in the QFT? And in some examples, I know how to do that, but not totally consistent. I don't think we have the best sense of like how do I explain what those resolutions are in kind of purely QFT language. There's certainly something physicists think about and are comfortable with. And it might just be that I need to bother the right people to tell me how to do it. I don't think that's yeah. All right. So I'm motivated to find what analog of this is true for other symplectic singularities. I mean, that's a hard question because we don't really know what the sort of full zoo of symplectic singularities looks like. At the moment, we have no idea how they're classified. For example, it's a very difficult open question whether we know the full list of compact hyperkähler manifolds, compact hyperkähler varieties. We might, but we know a few weird examples, and we don't have any good reason to think that those are the only exceptional examples. Almost all of them come from symplectic surfaces in some way. All right, so somehow like we have no idea how kind of strange the behavior of these varieties could be, but we know a lot of interesting examples, and we can see what happens in these interesting examples. There's sort of one other tractable situation that come from a relatively concrete example of one of these 3D field theories. And that's the 3D n equals 4 gauge theory that comes from a complex group G and a representation we call the matter representation. So the sort of key part here where there's new physics input is this n equals 4 bound. So that's telling us how much supersymmetry there is in the theory, or, so being a supersymmetric theory, there are these kind of extra odd operators, and n equals 4 is telling me how many of those are there and what are the relations that they satisfy. In particular, because we have this n equals 4, I end up with two distinguished twists here. And all of this stuff, and it's sort of like, I at some point convinced myself that this was a good explanation. These somehow have to do with the fact that spin 4 because there's an n equals 4 is SL2 times SL2. And these twists somehow have to do with the two different SL2 factors.
You should maybe say that 4 isn't the same 4,
It's not the same 4?
right? Oh, is it?
I thought it was the same 4. Right? Like spin 4 is the R symmetry, because, no?
That true? Okay, maybe that's right.
I mean, I'm not as confident as I should be, but it's the same.
You should know. Oh, I just thought that n equals 4 meant that there's 4 copies of some spin representation, right?
Yeah.
My understanding was like, there's some basic spin representation, and n is like, how many copies of it do you have?
Yes. The question is like, anyways, yeah, I might be embarrassingly wrong, you might be embarrassingly
I might be totally wrong, or more likely we're both right.
Or maybe we're both wrong. Anyways. All right. Anyway, from these two different, so note here, we have two different twists. And we get one of these symplectic varieties from a theory and a twist. So we get two different symplectic varieties out of the same theory. And these are what we call the Higgs branch and the Poisson branch.
Sorry, can you say again how you get us? So you're saying these two different twists give you two different Poisson algebras. The spec of those are two different symplectic singularities.
Yeah.
Okay.
Yes. Right. I mean, the point is these differentials, they're picking out some piece of the theory. Some of the like correlation functions in the theory that don't depend on position. Right? And so QA and QB, they're picking out completely different pieces of the theory. And these algebras are telling us sort of something about like what kind of questions we can ask that piece of the theory can answer. And so you get two things which don't have any obvious relationship. I'll just mention, like, you will often see these defined as part of the moduli space of vacua. And what's happening here is the Higgs branch is the part of the moduli space of vacua that survives when you turn on this differential, the QB differential, and the Coulomb branch is the part of the moduli space of vacua that survives when you turn on the QA differential. And I think this is actually one of the things which has confused mathematicians for a long time, that they've been looking at the wrong definition of the Higgs and Coulomb branches, and that it's actually more natural to think of them as coming from these twisted theories. I mean, at least that was a source of confusion for me, because I somehow thought this whole moduli space of vacua was. All right.
Sorry, wait, can you say that you thought the whole moduli space of vacua was important, but
yeah,
actually it's not?
Well, I mean, it's important.
But sorry, what's the other perspective you're advocating?
The perspective I'm advocating here is think about these twists as sort of the important things, right? And the mixed branches,
yeah,
the twists just don't know neither twist knows they exist.
Yeah.
That's all I do.
I see. You just want to consider them independently rather than kind
Yeah.
of putting them together.
Yeah. Well, that right, when I ask for other things about the A-twisted theory, that will have something to do with the Coulomb branch. And when I ask for other things about the B-twisted theory, that will tell me something about it. You've written papers about this, right?
Yeah, but I'm interested in the perspective you're advocating.
Yeah.
I saw a talk once by, I forget who it was. It was maybe Tudor, who claimed that kind of Higgs and Coulomb branches are both kind of coming off of each other, and kind of you should imagine kind of it's like what happens when you have a singularity and there's like a derived bit coming off of it or something. I don't know if there was any justification for that, but or if I'm remembering.
It's an interesting story. Okay, when should I stop?
Around 5?
Yeah, maybe I'll just say, this A-B part, that's very sort of suggestive. That sort of suggests there should be some kind of, so if you know a little bit about mirror symmetry, you might know it involves switching something called A with something called B. But that's a two-dimensional field theory story. But we would expect there to be a similar thing here, where I swap these two. So I find some other field theory where there's an equivalence between the two theories and it swaps the two twists. And doing this for two-dimensional theories is the kind of physics background behind mirror symmetry in the sense of Pensevich, et cetera, relating a Fukaya category, that category equivalent achieves. And here it's the same thing, but there's an equivalence between two different theories that swaps these twists. But it's just sort of mathematically different because it's 3D theories. We're running pretty low on time, so let me try to speed up. You should actually think of this as fitting in with other dualities in physics, so homological mirror symmetry in dimension 2 and geometrical identity in dimension 3.
We could go 5 minutes more because we started late.
Well, that's true, but that's all right. Oh, yeah. Maybe I won't speed up. Sure, you can see, I don't have that many slides. All right, so I should say something about what these are. Higgs branches can be realized as symplectic reductions of T star V, and that's with respect to a complex group. So if you're using a compact group, you do a hyperkähler reduction. And you can think about this quantization of them by replacing T star V with differential operators and doing non-commutative. So actually, for a long time, I thought the Higgs branches were easy to study because I was doing like a concrete thing where I actually understood the mathematical operations. And then when I looked at this stuff about Coulomb branches, they would say, well, it's kind of like this guy where you take the dual torus, Langland's dual torus, take its cotangent bundle and mod out by the bundle group. It's kind of like that. But you'll note that doesn't depend on the representation. That's kind of upsetting. I say, oh, well, but it does depend on the representation. There's some quantum corrections. That's the classical Coulomb branch. That's not the Coulomb branch of the quantum theory. But we actually can describe the coordinate ring of this guy. And I should, and again, the directions required to say that this was done by Braverman, Finkelberg, and Nakajima, who found a sort of geometric description of what these quantum corrections were. Saying there is a purely algebraic way to define what these are, but it's a little bit complicated. It's not so easy to do that. But it ends up being, you can think of it as the homology of some space constructed from the affine Grassmannian. And we had talked about how this quantization comes from turning on an S1 action. So there's a loop S1 action, or a loop C star action, Grassmannian, and you get the quantization by adding that, taking the equivariant homology perspective. And it really is directly circuit. There's some actual kind of physical thing going on where it really is, you have some three-dimensional picture. All right, what sort of things can you get? These are my sort of go-to examples. If I take C to the n plus 1 and take the U1 acting diagonally, while doing the symplectic reduction, I'll get, and Asalata, forgive me, I have mixed together resolutions and the affine guys. So I get T star Pn as the resolution. The affine guy would be matrices of rank no more than 1. And on the Coulomb side, I get this quotient of C2, or its unique pregnant resolution if I do the result version. If I put in instead C to the n plus 1 and look at all diagonal matrices with determinant 1, that's what I mean by U1 to the n, then these guys swap places. the Higgs branch will be C2 mod the cyclic group, and the Coulomb branch will be T star P. Again, after you do a suitable resolution. If I take matrices times the fundamental representation and take GLN, and GLN is acting on matrices by conjugation, I get the symmetric power of C2 on both sides. This guy is self-dual. There are generalizations of this where I can get sort of combine these examples and get sim n of this quotient singularity. Those are all affine, as she mentioned. There's another one of these. This is maybe impossible to decipher. The better way to describe this is to draw the quiver in the physicist style, which is I have n in a box, and then n minus 1, n minus 2, n minus 3, all in circles. And that means my gauge group is the product of the GLNs for these circles. And then every time I have two numbers connected by an edge, I take matrices where the numbers of the two ends are the number of rows and the number of columns. And so here I have a copy of matrices where I'm only acting on one side, not acting with GLN. I'm just taking n copies of the fundamental representation for n minus 1. And when I do that, I get the nil cone on both sides. This guy is also self-dual. All right, and sort of funnier one you can take is 0G. So this isn't very interesting on the Higgs side. You're looking at like a point on G. Probably I should actually do some derived thing, right? I had to apply the moment map, get a derived thing. On the Coulomb side, though, I get the total phase space. So I get quite interesting space over there. And for quiver gauge theories, I can get Nakajima quiver varieties as Higgs branches. That's really the definition of Nakajima quiver varieties. And at least in finite type on the right-hand side, I get affine correspondence spaces. And this is sort of suggesting that we found some dual pairs of theories, or self-dual theories, as the case may be.
What are 1, 2, 3, and 4?
They're like which row? Okay. Right, so the first two rows are dual to each other. All right. So now we want to find out something about the representation theory of these algebras. So again, I had sort of thought that the way to do this would be easier on the Higgs side. That you would be thinking about D modules and doing some reduction. You're on sort of the Higgs branch. These are a little inconvenient to work with because you don't have the 6-functor formula. Sort of no obvious things you can take maps between. So a lot of these kind of standard techniques in geometric representation theory, you can't really do, but you can still find out some interesting stuff. Basically, you can use sort of more usual D module stuff before you reduce, and then maybe you won't do that much damage when you do the reduction. On the other hand, on the Coulomb branch, you should do something much more algebraic. So there's a natural big commutative subalgebra. And you can sort of analyze the representation theory of this algebra using this big commutative subalgebra and find out very interesting stuff, which I'll probably talk about more tomorrow. But interestingly, these two very different stories end up giving you the same common. So the kind of relevant thing to study, I said highest weight U of G modules, is that I take a version of category O. So I have a grading that I ultimately want. Oh, sorry. Let me step back for a moment. So category O, that's something that depends on a Borel, right? It's at highest weight. Well, I have to decide which way is higher and which way is lower in order to do that. So I have to choose some auxiliary data. And here, this is going to be what I'm calling a grading element. So an element where taking bracket with it is semi-simple with integral eigenvalues. So this is the quantum version of a Hamiltonian torus action, right? So if I go to the semi-classical world, I'd be taking Poisson bracket for the function, and that being integral, having integral eigenvalues is exactly telling me that that function generates a circle action. Maybe if you want to look at that. All right. So, somehow geometrically, the thing I should be thinking about is having a Hamiltonian circle action on my graph. Given that, I can define a category of modules where this grading element has finite length Jordan blocks, finite dimensional eigenspaces, and eigenvalues that are bounded above. And I mean, like in the real part, they could be complex numbers. And this category, well, it depends on two things. It depends on which quantization I choose, and it depends on my circle action. And it's sort of going to be nicest if this quantization I choose is integral in some appropriate sense. This goes back to Ben's point about more Sommerfeld conditions. But sort of it's going to be nicest when this guy hits some integrality. These parameters actually swap roles when you switch between these. So the data of choosing a quantization on the Higgs side gives you a C star action on the Coulomb side and vice versa. So a kind of natural thing to compare is category O for the Coulomb branch for one set of parameters. Swap the role of the parameters. Think of the C star action as giving you the quantization. Think of the quantization parameter as giving you the C star action, and looking at the Higgs subject to certain hypotheses that I'm going to sweep under the rug. In this case, there's a purely sort of combinatorial graded algebra that you can reconstruct both these categories. But not in the same way, in such a way that they're Cauchy dual. So this algebra shows up, it's the X of simple modules on the Higgs side, because I'm computing the D modules and I can compute the simple things. And it's the endomorphism of projectives on the Coulomb side, because I can sort of diagonalize this big commutative subalgebra, and that naturally gives me some projectives. So I don't get equivalent categories, I get equivalent categories which are, up to some issues about grading, derived equivalent in a way that switches simples and projectives. Well, note, if you sort of go back to this question about how to write characters of interesting modules, that tells you it's really the same problem in both of these categories. It's very much in my way.
Sorry, I didn't miss something, but the statement seems asymmetric in C.
I'm sorry? The integrality. Yeah, probably I should have put for C and like that. Sorry. Yeah, sorry, this is, I had some old slides and I modified them. I modified so yeah,
Is
you
the
want
theorem
this
no
to-
longer true if you remove the integrality assumption?
no, it's no, I mean, for a generic quantization parameter, category O will be semi-simple. And like it won't be semi-simple in like the same way.
It won't be semi-simple when it's exchanged by total duality.
Right, right. I mean, somehow, yeah, it's not. Yeah, I mean, somehow on the Coulomb side, I can like tell you exactly what happens at the non-integral parameters. And like what happens is, somehow you like choose your quantization parameter, and that gives you like some subgroup of your group and sub-representation of the restricted representation. And the category O for that more singular parameter is going to be Cauchy dual to the integral category O or the Higgs branch of that smaller group and smaller representation. So like, yes, in the extreme example, like the group and the representation are trivial, and you get that everything is simple and kind of boring. But the intermediate cases, it doesn't work out. I mean, this is like, so for example, one quite interesting special case of this is when you take the Cherednik algebra that corresponds to GLN and this, you know, the matrix representation times the fundamental. When you pass to like, you know, what are kind of rational parameters in Cherednik terms, what happens is you take a sub-representation that gets you an affine quiver variety for a bigger loop. And you get the sort of somewhat singular blocks of category O of the Coulomb branch there. It's Cauchy dual to category O of the Higgs for that quiver variety. Right, and that's not at all like a singular category O for the.
But there's still some statements,
There's still some statement,
but it's not this.
but it's not this. In particular, it's very hard to control the singular cases on the Higgs side. I don't really know what happens in that case, because that's like, you're getting some twisted D modules where like, I don't even know how to construct good examples of them easily. So I can improve the statement to include like all blocks. Yeah,
Will you say no or later? I don't know.
I mean, I have no more time to say anything else. I'm already over time.
Well, we love to hear you talk.
Well, that's it.
I mean,
Otherwise, you spent the last hour for that.
yeah. No, but how you say vaguely that these are reconstructed from T? Can you give us a hint? What is
Well,
it?
like I said, on the Coulomb side, it's literally the representations of T.
Okay.
And on the Higgs side, the T is the X of some semi-simple module.
Okay.
Sorry, I'm laughing in part because I had literally had that written on the slide and I was like, that's too complicated. I'm gonna sort of make it a little more vague, and that's exactly why I ended up with this issue of not assuming that my name was independent. Anyways, does that answer your question?
It does, yeah.
Okay. All right. So one of the cool things about this is this algebra of T, well, it's the X of some simple module, so it's graded. But the Coulomb category O isn't graded in any obvious way. So this T gives me an actual extra grading on it. And that lets me kind of do this Kazhdan-Lussig theory for category O. So in the sort of Coulomb category O, I have some version of Verma modules, and you can describe the multiplicities of simples in terms of canonical bases. Unfortunately, you know, it's not quite as nice as the Kazhdan-Lussig story. It's not like just taking intersection homology Schubert varieties, but it comes down to I do some geometric push forward and I look at how the push forward breaks up under decomposition. And you know, so I'll get some category of simples bigger than category O, where the simples in the category correspond to the sheaves that show up in this push forward, for example. And this is sort of a common way for canonical bases to show up. For example, canonical bases and representations of Lie algebras show up this way for Nakajima varieties. Or I should say actually for, let's just say that. For the quiver gauge students. All right. Any questions?
So in the standard category, this kind of enormous, they do appear like purely combinatorial from the